So thanks so much for this invitation, Anita, to give these lectures. It's really nice to be back at ISI giving a lecture series. That's where I was an undergraduate, and it's always great to come back and to talk about this topic, which is something that I really care about a lot. So just a moment. This is going to be a series of 4 lectures on the broad theme is higher categories in geometry and physics. And today's talk is going to be an introductory talk, which is an introduction to what higher categories are and why we should care about them at all. So the lectures are going to be mainly focused on sort of telling you why you should care about higher categories in geometry and in other areas of mathematics, and not so much focused on the technical foundations of higher category theory, which is a whole subject in itself. So I'll give you a flavor of that technical foundation, but I won't be giving detailed proofs of how things work. Right. So today will be the day when I'll talk a little bit about those foundations, apart from giving motivation. Okay, so let me get started. If something is not clearly visible or if I'm not clearly audible, just stop me if you have questions and so on. Okay, so there's going to be, the outline for today's talk is as follows. There's going to be 3 parts. So the first part is going to be motivation. Then I will talk about models for higher categories. And finally, I will give examples. Okay. And so I'm going to assume that everyone is familiar. Okay, so you can stop me if anyone wants a definition, you can stop me even now. But what I've assumed here is that people know what a topological space is. So I don't know if there are any undergraduates here and so on, but I think everybody would have seen a topological space. And I'm going to assume for today's lecture that we know what categories are, just the definition, categories and functors between them. So if anybody would like me to recall that, I'm happy to do it. So, so if there are any undergraduates, anyone, don't feel shy to stop me. But I'm just going to go ahead for now, assuming that we know what categories are. So, so let's start with the motivation. So the motivation, I want to start by talking about, so this whole subject, so what is higher category theory about? It's about, so you can think higher category theory or higher algebra is about the following thing, that in algebra we use, one way to think about it is that in algebra we usually write equations on a line, right? You write things, x times y equals y times x and so on. What if instead you could write symbols on a plane, and for every configuration of symbols, you could combine them and get an answer? That sort of structure would be a 2-categorical structure because it has 2 directions of composition. You can compose along the x direction and compose along the y direction. You could now imagine doing this, drawing your equations, your symbols on a 3-dimensional manifold, and ask how you can combine those symbols to get some output. You take some inputs, x, y, z, and so on, and you combine them. But for every configuration on the manifold, you should get some answer. Very roughly speaking, this is what n-category theory is about. It's about an algebra that is governed by, not by things written on a line, on a 1-dimensional object, but by things written on a higher dimensional manifold. That's one way to think about it.
So,
yeah.
Pranav, sorry to interrupt. I think there's a message in the chat box saying that somebody wants you to recall the definition of.
Oh, sure. Great, I can do that. No problem. Okay, so before I go ahead, then I'll just recall what categories are. So here's a definition. Oops. So a category C is given by the following data. So I won't write complete sentences. I'll just say out loud what I mean. It's given by 1 collection objects of C, a set. This is called the objects of C. And for all xy objects in C, you have some set cxy which is called the arrows from X to Y, or morphisms from X to Y. And I'm writing it suggestively as an arrow pointing from X to Y. And third, if X, Y, Z are three objects, then you have a composition map, a map from C, Y, Z times C, X, Y to C, X, Z, which satisfies, so let's write this as G, F maps to G composed with F, which satisfies associativity. Which is to say that if you multiply three things in two different ways by bracketing in two different ways, you get the same answer. Oops. Oops, again, I made the same mistake, I'm sorry. H composed with G composed with F for all triples, okay? So for all H, G, F arrows, this should be true. And oops, I left out a piece of data here. For for all X, you should have an object, an element, identity X in CXX. And you want that identity of Y composed with F is equal to F, which is equal to F composed with identity of X for all F arrow from X to Y. Okay, so that's the formal definition. So you have a collection of objects, arrows between them. You can compose two arrows to get a third arrow, and that composition is associative and has identities. Okay, so let me give you some examples. So you could look at top. This is a category which objects of top are compactly generated topological spaces. And the morphisms, so the arrows, so top from X to Y is continuous maps from X to Y. Another variant of this, which will be important, so I'll just introduce the notation, will be top star, which is objects of top star are base topological spaces. Pairs X comma X with X a point in X and X a topological space. And maps in top star from X comma X to Y comma Y is continuous maps X to Y such that F of X is equal to Y. That's another important example for today's talk. Here's another one. You can take vector space. You can take K to be some field, and you can look at vect K. So the objects of vect K are vector spaces over K, and vect K of V to W is linear maps. And in each of these cases, it's obvious how to compose two arrows. You can compose continuous maps, you can compose linear maps, and so on. So just some notation. Sometimes we write, oops, what did I do? Notation. Sometimes we write Hom CXY is CXY. And sometimes we also write maps from X to Y. Okay, so these are some examples, and you can cook up a lot more. You can take groups and group homomorphisms, rings and ring homomorphisms, modules and module homomorphisms, and all of them have a composition that's associative. and so on. So let me describe also another class of examples, which will also be important for us. This is more like, instead of saying a class of examples, let me say types of categories. So here are some. So in the previous examples, categories were used to organize a class of mathematical objects, groups, topological spaces, and so on, into a mathematical object of its own right, a structure. But we can also study categories themselves as objects, as interesting mathematical objects, just the same way that we study rings, modules, and so on. So these are going to be of that type. So let me give another class of examples. So a category with one object. So groups are the same thing as categories with one object. Category C, such that not groups, monoids. Monoids. So monoids are the same thing, if you think about it, as categories C with objects of C is just a point, single object. So if I have a category with just one object, the set of arrows from that object to itself has a composition, a multiplication, which makes it into a monoid. Then I have groups. These are monoids with every element invertible. So they're categories with one object. Then you have groupoids. These are categories in which, with every object invertible, every arrow invertible, this means that for all f, there exists G such that f composed G is equal to G composed f is equal to identity. Okay, suitable identity. Okay, so these are some examples. Here's the final example that will also be very important for us. So we will look at posets, partially ordered sets. So a poset is nothing but a category.
So just a quick question about groupoids. So is it that, do you mean self arrows are invertible or?
No, all arrows.
Okay. So F composed G typically is identity on one space or identity X, and G composed F will be identity Y.
Yes, that's why I said a suitable identity. So this will be identity on X, and this will be G composed F will be identity on Y.
Okay. Thank you.
A poset is a category in which there is a unique.
Can group be an example of groupoids in this category? Like
exactly, a group is a groupoid with one element, with one object.
Okay.
A poset is nothing but a category C. Okay, let's call it P, such that. Okay, let's call it C, just so we don't have any confusion about notation. A category C such that for all xy objects, Cxy is either empty or singleton. Well, not the same singleton, but a varying singleton. So, or singleton. So if you have a poset, if you have a partially ordered set, you can define a category from it. The category has objects, the elements of the poset, and you put a unique arrow from X to Y if X is less than or equal to Y. So X less than or equal to Y is the same thing as arrow from X to Y. Okay. So posets are also examples of categories. And you can try to think about what various things mean in this language. For example, what's a representation of a group? It's just a functor. And okay, so I didn't define functors. I mean, if functors are the natural maps between categories. Okay, so I think rather than writing out the entire definition, there won't be time for that. So I'll just let you figure out what that should be. You know what a group homomorphism is? It's something that preserves the multiplication. So a category homomorphism is something that sends objects to objects, arrows to arrows, and preserves the multiplication. Okay, so these are what categories are. And now you can ask yourself things like, what is a group representation, for example? A group is a category of one object. A group representation is just a functor from the group thought of as a category to the category of vector spaces. It sends the point to a vector space and it sends the arrows to the representation. So a lot of mathematics can be formulated this way. In fact, ring theory and so on, rings can also be described using as categories. So my point here is that we often encounter categories the first time we encounter them as some way to organize other mathematical objects. But the mathematical objects we're studying are themselves also categories. Right? So categories are quite universal in that sense. Okay, so we'll use this as we go along. Okay, so someone asked me for the definition of category. Is this was this satisfactory as an answer?
Yes, sir. Thank you.
Okay, great. Right. So keep all those examples in mind. Now, I want to talk about. I want to motivate higher categories. Right. So why do we want to study higher categories? There are many ways to motivate this. There are many places you could start to motivate this. One way I could motivate this, which I'm not going to do today, at least not right now, is to say that let's ask. We saw that groups, topological spaces, etc., form categories, and I could ask the question: what do categories form? Now, if you have two categories, you have functors between them. But it turns out there are also maps between functors, which are called natural transformations, right? So this is the first example of a higher categorical structure. Categories themselves naturally organize themselves into something where you have objects as categories, arrows as functors, and natural transformations between functors. If you have not thought about this before, I can tell you what it is for groups. So if you think of the subcategory consisting of groups, a functor between groups will just be a group homomorphism. And a natural transformation between functors will be conjugation. So two group homomorphisms that are conjugate will, if you're given two group homomorphisms, you can ask if they're conjugate to each other. And an element that conjugates one to the other would be a natural transformation. Okay. So categories organize themselves into some structure, which is more naturally thought of as some two-dimensional structure. And I may talk about it later, but if there's time. But let me, for now, go to the main example, motivating example that I want to motivate by, which is homotopy theory. So today I'll talk about homotopy theory as the motivation, and later in this series of lectures, we'll see that in fact there are motivations coming from algebraic geometry, symplectic geometry, representation theory, and so on. So there's a certain sense in which higher category theory is a generalization of homotopy theory, and that's what I want to explain now. So what is homotopy theory? In homotopy theory, you study spaces. So study space, you study some spaces X. But now I haven't said what spaces. You might think topological space. That could be an okay answer, but that's not, that doesn't capture the essence of what homotopy theory is about. Because when you study a topological space, you have point set topology, right? You have points and you have, you can talk about neighborhoods and open sets and so on. But that contains more structure than what I'm interested in. So for example, I would want to declare two spaces to be equivalent if I can stretch and mold it until it becomes the other space, right? So for example, if I take the real line, I can just shrink it down until it becomes a point. So the real line and the point are the same space in homotopy theory, but they're not the same space in point set topology. One is uncountable and the other has only one point. So what is it that homotopy theory studies? Homotopy theory thinks of a space as some kind of an object where you can talk about some basic entities, call them points, if you like. And it's interested in the question of joining points by paths, right? So you're interested in the notion of a path between points. But now you can organize, so let me just write that down. So you can study a space X as a setting where you have points, in quotes, paths between points, but once you have paths, the set of all paths should itself form a space. Then I can ask, what is a path in this space, in the space of paths? A path in the space of paths would be a path between paths. So you study paths between paths. Which are called homotopies. And so on. And now the set of homotopies that themselves forms a space, and you can look at paths, and so on. And so on. So here's a picture. You have a space, it has some points. You have a notion of a path between those points. But if I'm given some two paths, gamma 1 and gamma 2, a path between them would be a sequence of paths, if you like. Not a sequence, sorry, a family of paths interpolating between these two paths. And this is called a homotopy. It's a picture of a homotopy between. And this whole thing is sitting inside some big space. So like a torus. Okay. So how can we model this idea? So the question is, in homotopy theory, you want to study spaces as some objects where you can do these things. But the problem is, how do you model this? So one possible way of modeling this is using topological spaces, although they will contain too much information. So can model this, can try to model this using topological spaces. So for me, the topological spaces will always be objects of that category top I defined. So they'll be compactly generated topological spaces. Okay. So let's see how to do this. So for this, I'm going to define, for a moment, I'm going to define this thing. Let me just define definition. I'm going to define this thing called the geometric n-simplex. Oops. N-simplex. And this is the following thing. You just define this topological space delta n. It's defined to be the set x0 through xn in Rn plus 1, such that summation xi, sorry, what am I saying? Okay, it's fine, I guess. In or n plus 1 is that summation xi is equal to 1 and xi's are bigger than or equal to 0. I guess I could have put the bigger than or equal to 0 over here. So let's draw a picture of this. So delta 0 is a point. Delta 1 looks like this. Delta 2 is the space, the triangle. Delta 3 is a tetrahedron. I won't be able to draw it as sitting in a higher dimensional space, but let me just draw a picture of what delta 3 looks like. It's a tetrahedron, and so on. Okay, so delta n is this topological space for every n, and now I can try to ask what a map from delta n into my spaces. So let X be any topological space. Then giving a map from delta, giving a map points of X is the same thing as giving a map F from delta 0 into X. Paths in X, well, this is the same as giving a map F from delta 1 into X, from an interval into X, right? Well, what is a map from delta 2 into X? So if I look at a map from delta 2, which is a triangle, let me label this 0, 1, and 2. And if I want to give a map from this into X, into some space, what do I get here? I'm going to get some path, another path, and a third path. So let's call this path gamma 0, 1, gamma 1, 2, and gamma 1, 3. And then the region inside is shaded. Because I mapped a triangle in there. So what you get is a path. You get two paths and a homotopy. So giving F from delta 2 to X is the same thing as giving paths gamma 0, 1, gamma 1, 2, gamma 1, 3, and a homotopy from gamma 1, 3, or the other way around, if you like, to gamma 1, 2 composed with gamma 0, 1. So by composition, I just mean you run the second path after the first path. Okay, that's the rule for composition. Right. So I have the structure and I can continue this. I can now look at what a map from delta 3 into X means. And this will correspond to some homotopy between homotopies. And so on. Ad infinitum, right? Okay. Any questions? Oh, I see there's a chat.
Pranav, one question. Are you considering only pointed spaces or general spaces?
I'm considering general spaces right now. Later, I'll specialize to pointed spaces.
Okay, thanks.
Yeah. Okay. Someone had a question. Ob C may not be a set always, but a collection of objects in C. Yes, absolutely. So the point is, it depends in what set theoretic framework you want to work. That's a great, good you asked the question, because there was this thing that I wanted to say at the beginning. Yeah, so when you study homotopy theory, you're really studying shapes and not point set topology. Okay, so and that's the point I'm going to try to make. And I just showed you that the real line has uncountably many points, but the singleton point has only, has only one point, but they're the same space. You can contract one to the other. And Poincaré at the turn of the century, I mean the beginning of the 20th century, was studying topology and various things. I mean, he contributed to a great number of fields in mathematics. And he made this comment at, I think, the ICM in Rome, if I'm not mistaken, some Congress of Mathematicians in Rome, where he said that point set topology is a disease that humanity will soon recover from. Okay, and the question is, what did he mean by that, and why did he say that? Now, the point was that you see, when you invent a mathematical notion, you should ask, what is it good for? Like, why are you inventing it, right? I mean, you're doing it to do something with it. And a lot of what topology is invented to do is got nothing to do with point set topology, actually. So there are many, as I'll show you in this thing, there are many other ways to model homotopy theory, for example. So homotopy theory is one thing that topological spaces are invented to do, study shapes. They're also invented to understand the idea of locality, right? And for locality, if you really pursue that idea further, you reach the notion of sheaf theory, which Grothendieck realized in the, realized that what he realized was that really what you need to understand is the category of sheaves on the space and not the point set topology of the space itself. And that was really needed in algebraic geometry, because in scheme theory, you don't have topologies that are fine enough if you just study point set topology. You need something deeper, and that led to this whole thing called topos theory and so on. But anyway, the point I'm trying to make is that the kind of questions you run into when you start asking questions about the kind of sets that you allow and so on, those are things to do with the foundations of mathematics. Like we need to set up a language so that we can talk about everything else we want to talk about. And it just so happens that we have chosen, for historical reasons and various other reasons, Zermelo-Fraenkel set theory or some variant of it as our usual foundations. And in principle, in theory, everything can be built out of it, right? But mathematicians don't think that way. We don't think in terms of Zermelo-Fraenkel's axioms every time we do mathematics. And that's for a good reason, because that's just there to ensure that everything we do makes sense and is good. And yeah, so these kind of questions, yes, you're right. Objects-C may not be a set, but that has to do with what a set is and the foundations of Zermelo-Fraenkel set theory. And actually, I can make it a set if I use the axiom of universes. Okay, so if I use the language of universes, then you have these different universes. You can put one universe inside the other, and every set is a set. It's just a set in some sufficiently large universe. So yes and no. Ob-C is always a set. It's a set in some universe if I work with Grothendieck's axiom of universes. But the point I'm trying to make is these kind of things are more like technical issues that are sort of little misleading in the sense that they're not really deep questions. There are times, though, when being a set or not a set will matter. In other words, what size your set is it in a large universe or in a smaller universe, matters when you talk about things like the adjoint functor theorem and so on, right? So yeah, but I don't want to get into the set theoretical foundations because it's mostly a little misleading. It's not really relevant. I'll get into it only when it's really relevant to the mathematics, which is when I talk about things like the adjoint functor theorem. But for the rest of it, it's just a technicality and it's not so important. And as I was going to say, point set topology itself is not that important for what we're going to do. And the one more comment I want to make about that is that, in fact, there are other approaches to the foundations of mathematics that are homotopical in nature, that at their very foundations are more constructive. And there's a very important program that Voevodsky started. So Voevodsky proved a very important theorem, and he found an error in his own proof, or I think somebody else found it. I don't remember. But and that led him to reconsider the foundations of mathematics. And the foundations that he started off, he's unfortunately no more with us, but that he started off are based on homotopy theory. So the fundamental building blocks are not sets; they are shapes, if you like, and they obey some axioms. Yeah. So set theory is not going to be that important for what I'm saying. It's one possible foundation, but it's not too important. Yeah, but thanks for the comment. It's really connected to what I wanted to say. And so basically, you should think of Ob-C as a large set, a set in some large universe. Or if you like, a class, if you prefer Gödel-Bonnet's axiomatization. Okay, so let's now try to understand what this structure that I've talked about is giving us. So I've described for every n-simplex, I can look at maps, and it maps from the point give me points, maps from a one-simplex give me paths, maps from a two-simplex give me a composite of two paths and a homotopy between gamma 0, 2. Oh, sorry, I wrote 1, 3. It should be 0, 2. I apologize, and I should not have erased that. Gamma 0, 2, and this is gamma 0, 2. Okay, so let's try to understand what the structure is. And to do that, let me just describe, let me introduce some terminology. So definition, oops, there's been a power failure here. So just, I hope I don't get disconnected. Okay, so let me just turn off my video for the time being. Or maybe not. I guess it's okay. So here's a definition of the abstract n-simplex. So the abstract n-simplex, which is just, I'll denote it as n, is the category, the poset, the totally ordered set with n+1 elements thought of as a category. So it's this guy. And this picture is a little misleading because I have an arrow from 0 to 1 and a arrow from 1 to 2. I can, of course, compose them and get an arrow from 0 to 2. So it's probably better to draw a picture that looks like this. So the 0 simplex 0 is just 0. The 1 simplex is 0, 1. And of course, there are identity morphisms. Identities are not shown. Then you have the 2 simplex, which is a map, which is this guy, 0, 1. You have a map from 1 to 2, and you also have the composite. So if I call this map F01, I call this F0, well, I should not call it F, okay. It's not the same F01, okay? It's a different F01 here, F12, F02, then you have F02 is equal to F12 composed F01, and so on. And so this is the abstract n-simplex. And in fact, the collection of all these guys forms a category, a subcategory of cat. So delta contained in the category of categories is the full subcategory whose objects are finite ordinals. So finite ordinals thought of as categories. So you have this full subcategory. So let's see what this means. This means, for example, that I have maps between these abstract n-simplices, right? The maps are just functors. So maps n to m are functors, or maps of totally ordered sets. So let's look at some maps. So for example, I have a map from 0. I have 2 inclusions. I have D0, which is the map into 0, 1, which is the map 0 goes to 1. Then I have the, oops, sorry, this should just be like 0 itself. And then I have the map from 0 to 1, which is 0 goes to 0, and this is D1. And then I have, let's look at maps from 1 to 2. So these are maps from 1 to 2, 0 to 1. I can also look at maps from 1 to 2. Map from 1 to 2. Maps 1 to 2. I can write a bunch of them. So I can do 0, 1 maps by, sorry. I map it by D2 into 0, 1, 2, which is just 0 goes to 0, 1 goes to 1. And I can do 0, 1 maps to by D1 to 0, 1, 2. This is 0 goes to 0, and 1 goes to 2. And so on. I hope the picture is clear. Let me just write all of them here. So 0 goes to 1. For this one, I'll write all of them. 0, 1, 2. And this is 0 goes to 1, and 1 goes to 2. So they're order preserving maps, right? So I'm just writing all the order preserving maps that are injective in this case. Of course, I also allow non-injective maps. So there are surjective maps, but every map can be factored as a surjection followed by an injection. So yeah, I'm not writing all of them. So these, you see, you have these 3 face maps, and if you think of it geometrically, it's like the inclusion of the 3 faces of a triangle. You have 0, 1, you have this F01, F02, and F12. Right. So if you think about what it's doing to arrows, it's basically the inclusion of these of the 3 faces. Okay, so I define delta. So let me now define a simplicial set. A simplicial set. Okay. Should I define functors, or can I? Everybody knows what a functor is. Okay, stop me if something doesn't make sense. Okay, someone has written. Obscene. Oh, so yeah, that's true. So some sets can be obscenely large. Yeah, yeah. And obscene is obscenely large. I just read Suri's message in the chat. Yeah. Okay. So let's make a definition. So simplicial sets is a category, and it's defined to be the category of functors from delta op, this category delta that I just defined, to sets, to the category of sets. I forgot that category of sets is probably the most basic example of a category. I didn't give the example. So so what is this? An object of S set is called a simplicial set. And what is a simplicial set? X dot in objects of S set is the following data. It means that for every n in delta, I should have some x of n, a set. And this is on objects. And for all f from n to m, you should have a morphism x of m to x of n, which we'll call f upper star. Okay. This is what it means to give an element of an object in the category of simplicial sets. And the morphisms are also defined in the obvious way. So I mean, as maps from xn to yn, if x and y are two simplicial sets, it would be a collection of maps from xn to yn that are compatible with these pullback maps, x upper star. So let's try to, yeah.
Is there a particular reason to take delta off? I mean, delta would work, or I mean, why are we taking delta off the opposite category?
Yeah, good question. So I could take delta, then I get something called co-simplicial sets. But what I'm doing is trying to explain this construction that I gave in the beginning over here. From a topological space, I built out this thing that for every n, I constructed maps from the geometric n-simplex, which is a topological space, into my topological space. So maps from delta 0 were points, maps from delta 1 were paths, and maps from from delta 2 were these triples of paths and homotopies and so on. And I'm trying to organize this into some structure to try and understand what is the structure that is underlying these collections.
Okay.
And it turns out that I should look at delta op. Why? You'll see in just a moment if you just hang in there for a second.
Okay.
Thanks. But the motivation for why I choose delta op is because I'm trying to explain. I'm not just making up a definition. I'm trying to understand the structure underlying this thing that I was trying to define earlier.
Okay.
I'm trying to axiomatize that. So that it happens to be that you need delta op. You'll see in a moment why.
I see. Okay.
Okay. So you have these pullback maps. Okay. So let's look at what this means concretely. So for example, if I consider these maps di, so a simplicial set. So maybe let me just say fact. Okay. So here I define these maps di. There are also some maps si. So let me just define those as well. So let's be over here. So in delta, we have the maps di from n minus 1 to n, which misses the ith element. So di of what should I call it? Di of k is equal to k for k less than or equal to sorry, strictly less than I, and it's equal to k plus 1 for k bigger than or equal to I. Okay, so those are one collection of maps. I showed you the DIs for the small values of the simplex size for n equal to 0, 1, and so on. I showed you what these maps are. And you also have maps SI. So these are injective maps. I also have surjections SI mapping n plus 1 to n, which with SI of k is equal to k, is equal to k for k less than or equal to I, and SI of k is equal to k minus 1 for k bigger than I. So for example, you could look at this map from 0, 1, you have a map S0 to 0, which just sends everything to 0. And from 0, 1, 2, you have a map to 0, 1. You have many maps. So what are the maps? SI. So I can let's do one example. Let's do S1. So S1 will send 0 to 0, 1 to 1, and 2 to 1. Okay. So you have these maps. And in fact, these maps generate all other maps. So you can write all the maps in this category delta as composites of SI and DI. And that is what is behind this theorem. So theorem, or actually this is not even a big theorem, but okay, let me say proposition. Proposition, giving a simplicial set, is the same thing, is equivalent to giving, well, what should I give? Sets xn for all n bigger than or equal to 0, maps di called face maps. Okay, I should call these d upper I or something. I should have called those upper I probably. Anyway, okay, let's call these boundary I from xn to xn minus 1, and s. Okay. Let's call these d. Actually, I should have called those d upper I's. I apologize. I guess I used it too many times. Okay, maybe not. Let me just do it quickly. Let's call these D1, D0, and so on. D2. Just changing the notation a bit because I would prefer to put the DI. Okay, so I should give these maps di from xn to xn minus 1 and si from xn to xn plus 1, satisfying some equations. And those equations are the ones that you can figure out from the properties of the category delta. Okay, so I'm not going to write them out, but I just want to say that it's actually something very explicit. For every n, we specify a set, and then we specify these maps between them. Okay, so why am I saying all this? Well, because there is a construction that takes an abstract n-simplex and produces a geometric n-simplex.
Can you go to the previous page a bit?
Yeah.
Yeah, thanks.
So there's a construction that takes, so there's a functor geometric realization, if you like, from n from the simplex category delta to the category of topological spaces, which takes n to the topological space delta n, and it takes the face maps. Those maps di's are called the face maps to the corresponding inclusions. So and the degeneracies si's to the corresponding maps between the geometric n simplex. So if I have a map f n to m induces realization of f from delta n to delta m, and this sends the sense f of x1, what was this, x0 through xn to x sub f of x0. So for example, the inclusion di, d upper I, did I mess this up? Yeah, no, I think that's right. So every basically the geometric n simplex is defined in the coordinate space, right? And so if you have a map between the indices of those coordinate spaces, between the bases, then you get a linear map between those coordinate spaces, and that maps the geometric n simplex to the geometric n simplex. So let me just show you some low dimension examples. So if you take the inclusion 0, 1 by d2 into 0, 1, 2, well, this should get mapped to a map between the geometric n simplex corresponding to the interval. It should give me an inclusion into the triangle. What is this inclusion? This is just the inclusion of the simplex as this face, where this is 0, this is 1, and this is 2. This is 0, and this is 1. Right? So each map in the category delta gives me a map of topological spaces. And this map is covariant. So I think Mamta was asking, why did I take delta op? So here I don't have delta op, here I have delta, it goes the same direction.
Yes. Yes.
But if I have a topological space X and I map into it, then the direction of the arrows gets reversed. So if X is a topological space, then Hom from delta n. So define a simplicial set. So let sing n of x by definition equal to Hom from delta n into x, right? So if I take this Hom, this thing is going to be a set of continuous maps. This is Hom and top. And this gets organized into a simplicial set. N goes to sing n of x is a simplicial set. And what I said at the beginning is that this simplicial set, so sing dot of x, maybe I should give a definition. Definition is sing dot of x is the singular Well, maybe may not a full sentence. Singular chains on X. This is belongs to S set, the simplicial set. Okay, so this is the simplicial set, and it encodes the homotopy theory as I described to you. So I told you that if you go back, if I can go back a few slides, what I told you was that giving the simplicial sets amounts to telling me what are the points of the space, what are the paths in the space, what are the homotopies between the paths in the space, and so on and so on and so on. What are the homotopies between those homotopies and so on. So if you were only interested in homotopy theory, if you wanted to understand how paths can be formed in the space and paths between paths and so on, another way to think about it is as being given by this singular simplicial set of that topological space. So it's another way to model the homotopy theory of the space. But in this way of thinking about it, it's kind of more explicit that I have some points, which are the zero simplices, the elements of Sing 0. Then I have elements of Sing 1, which are paths which go in a direction from the initial simplex to the final simplex. Then I have homotopies between those paths, which are thought of as higher morphisms, two morphisms. And I can stick two triangles together. I can stick two of the diagrams in this picture together to get a higher dimensional, I can get a tetrahedron, which is then, when I compose two such homotopies, they will form the boundary of a tetrahedron, and so on. Right? So let me just show you a higher homotopy would be something like, I have a tetrahedron in my space. This is some complicated space, and I have some curves in that space. Gamma 0, 1, gamma 1, 2, gamma 0, 2, and so on. And here I have a homotopy. Then I have another homotopy connecting gamma, this is 2, 3, to gamma 1, 3. I have another homotopy. And I can ask, how can I combine these two homotopies and can I compose them? And yes, you can. You can map a simplex, a 3 simplex, into the space, which is a homotopy connecting these two homotopies, and so on and so on. So the singular simplicial set is a model for this idea of a space where you have points, paths between paths, and so on.
I have a question, like in the definition of this norm F, should there be some zeros if n is less than m? So,
sorry, come again?
Can you go to the previous page?
This one?
So when n is less than m.
Yeah, maybe this is not quite right. Wait, hang on a second. So, okay, maybe I'm using this definition. So I'm saying that delta, I can also identify delta n with the set x1, x0 through xn. Wait, we said this is this summation xi equal to 1 and xi bigger than or equal to 0. Sorry. Yeah, what was your question? And then I was trying to define this map, so maybe I messed it up. Hang on a second. So I want to map n to m. Sorry. I think it should be this. So it's f of x0 xn is equal to y0 ym, where yi is the sum of over what should I say, j in f inverse of I of xj.
Thanks.
I apologize. There's another model for the n-simplex, and I was kind of mixing up the two things. Sorry. So this makes sense, right? Does this answer your question? The issue with the, I guess you were thinking the sum is probably not equal to 1. Sajid?
Yes, indeed.
Does this sort that?
Check.
Oh. Wait, have I messed up again? No, I think this is not right either.
So what is ym then? Like if m is
Yeah,
bigger
yeah.
than.
So, I'm sorry, this is not right. No, what do I want to do? Just hang on a second. So I want to map. It's just the inclusions of the various spaces. So we're just a bit confused about how to write it. Let's see. So.
Do you need n less than equal to m something, or is n?
No. N can be anything.
Okay.
So what do we want to do? We want to map. Let's see. We want to map. For example, this inclusion should be the one that goes from. It's from this interval to this interval, right? And I have 0, 1. So basically, this edge here goes to this edge. So, or maybe what I wrote first was. How to write this? I'm sorry, just E0, E1, and here I have E0, E1, E2, and so I map E0 to E0, E1 to E1. This is just, so this map F from N to M induces F from Rn to, well, F tilde from Rn to Rm, right? By just mapping the basis element EI to the basis element F of, the corresponding basis element.
Yeah.
And 0 otherwise. And I'm claiming that maps the simplex to the simplex. Is that, so F, sorry, I don't know why. Just one moment, let me turn on.
It's just the convex hull, right? The simplex of these EIs.
Yeah, it's the convex hull of the EIs. So what am I doing? So I'm sending F of EI is E sub F of I. And that maps EIs to EIs, and you look at the induced map on the convex hull of these points. Have I written it right? So E0 maps.
Whole of this thing like del M.
Sorry?
I mean, according to this map, I think it may not be whole of the convex hull of the target space which you have written, del M.
Yeah, it will not be exactly. So for example, here it's not, right? 0, 1 maps to 0, 1, 2.
Yeah.
The edge is included into one boundary of that space. In this picture, it's this thing gets mapped to this.
It's okay.
So it's the induced map on the convex hull.
Yes, yes.
Yeah. Yeah, sorry, I wrote something confusing before. It's just just take the linear map induced by the thing and then take the map on the convex hull of the points. Okay. Singular chains on X. What was I saying? Yeah. So I constructed a simplicial set for you, and it encodes this idea of homotopies between homotopies and so on. Now you can ask what special properties does sing.x have? So is it any arbitrary simplicial set? Can every simplicial set arise from a topological space in this way? Or do the ones that arise have some special properties? And I claim it does have a special property. So let's make a definition. We take we define this simplicial set from delta op. Let me write it differently. So we define, so for all n, I'm going to define delta underline n from x, sorry, from delta op to sets. It's just a functor which sends m goes to hom from m to n in delta. So it's the functor represented by n. So this is the also the abstract n-simplex, just thought of as a functor from delta op to sets. And so now we can define wedge nk contained in delta n is the full subsimplicial set. Which I'm just going to draw a picture to explain what it is, which is the union of faces not containing k. So for example, delta 2, 0 is equal to this. So it's not containing, it's all faces in delta 2 not containing 0. So it's, we have 0, 1, and 2. So I want to delete the face opposite 1, the face containing, sorry. I want to delete the face, oh sorry, not of all faces containing k. So I want to delete this face. Okay, so this is the horn. This is called a horn. And so this is delta 0, 2. What is delta 1, 2? This is this guy. And delta 2, 2 is this guy. So it's the full simplicial subset. So inside this functor from delta op to sets, you look at all those homomorphisms from m to n that factor through these faces. That's what the n, the horn is. Okay. So now, if you look at the geometric realization of the horn, you see that if you give a map, if I have a map from the geometric version of this thing, which is, let's say, this guy, what was my first one? 0. To some space x. What does that mean? That means I've given a pair of paths, gamma 0, 1 and gamma 0, 2. But I can always fill it out. We can always extend it to a map from the full simplex, the full geometric simplex, to my space. Right? Because this guy is a retract of this guy. You have an inclusion and you have a retraction map. You can just squash away the triangle on down to the V-shaped guy. And so you can just define the map by composing with the existing map, the projection map. So you simply extend F by setting F tilde equal to F composed with R. Right? And this is true in general. The n tetrahedron can be retracted onto the union of any of its faces. If I remove one of the faces and look at all the other faces, I can retract the whole tetrahedron onto those faces, the remaining faces. So right. In general, okay, so to make the general statement, let me make a definition. So let X dot be a simplicial set. And the geometric realization of X dot belonging to top is defined as follows. The geometric realization is the co-equalizer of the following two things. You take the co-product. Oh, there's no space. Let me just make more space. The geometric realization of X dot is the co-equalizer of you take the union of X n cross delta M, and here you take the union of Xn cross delta N. So what am I trying to do? For every abstract n-simplex, I put in a copy of the geometric n-simplex. That's the right-hand side. So this is n in delta, in this category delta. And on the left-hand side, I'm taking one for every arrow in delta. So this is for coproduct over arrows of delta. And if I'm given an arrow, I can do two things. Well, these are over arrows from n to n. Or from, let's see, m to n. Right. So if I have an arrow from m to n, I can do two things. I can take, so this is basically the coproduct xn cross delta n divided by an equivalence relation, where I identify an element x, comma, a simplex, maybe call it sigma, sigma, comma, a point x is sigma, comma, f lower star of a point x is identified with f upper star of sigma, comma x for all f mapping n to n. So in other words, what you want to do is you want to put in a copy of an interval for every one simplex, a copy of another interval for every other one simplex, and so on. And then you have a copy of a triangle for every two simplex. But then you want to say that if the boundary, if the face of this two simplex is supposed to be the same as this one simplex, then you should identify the two of them. That's what this is saying. Anyway, this is something you really have to sit and meditate on, this definition, but this is the formal definition. So here's a fact. Some easy lemma you can prove is that this is an adjunction. So you have top to simplicial sets, and you have this map, which I called sing, and I have this map, which I called geometric realization, is an adjunction with this being the left adjoint. So what does this mean? This means that Hom in top from some space X to the singular simplices on some space Y is isomorphic to Hom from geometric realization of X to sing Y. Okay, so so this is a easy thing to prove, but you have to just sit and work through this. So I define geometric realization. So now, what was it I was saying earlier was that I can define this abstract n-simplex, and its geometric realization is a retract of the geometric realization of the real n of the standard geometric n-simplex. So the geometric realization of delta n, this underline n, is just the geometric n-simplex. And the geometric realization of this guy is a retract of the geometric realization of delta n. That's what I was trying to say. So any map from this guy, geometric realization of this horn into X any topological space, can be extended to a map or from geometric realization of delta n, which is the geometric n-simplex to X. So what's the upshot? So what we have proven essentially, so the theorem then is that, maybe I should go to the next slide actually. Or okay, let me make a definition here and then I go to the next slide. So the definition is a simplicial set is a Kahn complex, is a weak Kahn complex if for all k and n, the inclusion delta nk into delta n simplicial set X, maybe Y, induces an isomorphism, induces a surjection Hom delta n y, which is nothing but yn by the Yoneda lemma, to Hom wedge k n y. Okay. And
sorry to interrupt again.
Yeah.
I have a confusion in the adjunction which you wrote. So please, can you please go back?
Right here?
The adjunction.
Yeah, this is it.
Yes. So sing is the left adjoint. So
is the right adjoint.
Okay, it is a right adjoint. So
sorry.
Yeah, yeah.
Thanks. Thank you. That was a mistake.
Yeah, yes. Thank you. Yes.
Yeah. Okay. So I'm using the Yoneda lemma here. Maybe I should. I don't know if I should explain that. I don't know if I have the time actually, but I can. The point is that maps from the abstract n-simplex into Y are just the same thing as the n-simplices. This is a special case of this thing called the Yoneda lemma. Maybe I can just write it here. Lemma is that for any category C, again, this is an easy exercise. For any category C, the functor H from C to functors from C op to sets. This right side is called presheaves on C, which sends an object X to Hom from blank into X is fully faithful. Well, this thing is called HX. And the way one proves this is that this is a consequence of Hom in pre-sheaves on X, on C, sorry, from Hx to any functor f is f of x. And this is a special case of that because delta n is nothing but h sub n. Is the functor represented by n. It's, in other words, it's Hom from blank into n. So if you take homomorphisms in simplicial sets from delta n into some simplicial set y, that's just the same thing as the n-simplices, just y of n. And this condition is that this restriction from Hom delta n y to Hom of the horn, which is the sub-simplicial set consisting of all the faces, should be a surjection. That's what the definition of a Kahn complex is. So the map from the n-simplices to the horns should be a surjection. Anyway, this is all some technical stuff. I think what I've told you is the intuitive meaning of this is that every n-simplex, every time you have a map from a picture like this into your space, you can extend it to a map from the entire triangle to the space. Similarly, if you have a map from the faces of a tetrahedron except one of the faces into the space, then you can extend it from a map from the solid tetrahedron into the space, and so on in all higher dimensions. That's the that's the content of this definition of what a weak Kahn complex is. So the proposition that we just sort of proved by pictures is that Sing X is a weak Kahn complex. Right? And the intuition is that we can think of the elements. Okay, so let me make a definition. An infinity groupoid is a weak Kahn complex. Okay, and the intuition here is that a weak Kahn complex had elements which are vertices. So the objects, so this is like a category which has, so an infinity groupoid, so intuitively, an infinity groupoid X dot has objects, the set X0, one morphisms, the set X1, two morphisms, which are morphisms between one morphisms, which is the set X2, and so on. And composition is defined as follows. Composition of one morphisms is the fact that if you have a triangle, if you have a map from here to here and a map from here to here, gamma 0, 1, gamma 1, 2, one simplices. So if gamma 0, 1 belongs to X1, gamma 1, 2 belongs to X1, then you get a picture like this, which belongs to, then you get this thing, which belongs to Hom from the wedge 2 of 0, 1, and 2. So this is, I'm missing opposite 1, wedge 2, 1 into X, which extends to a map from like this, gamma 0, 1. To X, and we think of gamma 0, 2 as a composite. So this is a, I mean, more precisely, we can say that this is a i.e. an element in X2, and we think of gamma 0, 1, if we call this element sigma, which is by definition the boundary opposite the 0, 1, the two face of sigma. Oh, sorry, I made a mistake here. We think of gamma 0, 2, which is by definition the boundary opposite the one face of sigma, as the composite, as a composite of gamma 0, 1, which is by definition the D2 boundary of sigma, and gamma 1, 2, which is by definition the D1, sorry, the D0 boundary of sigma. And we think of sigma as witnessing the fact that gamma 0, 2 is a composite of gamma 0, 1 and gamma 1, 2. So this is how we think of it. I mean, the definition is what I said, it's just a weak non-complex, but we interpret this to mean that the two simplex witnesses the fact that gamma 0, 2 is one possible composite. We're not specifying the composite uniquely. We're specifying one possible composite of gamma 0, 1 and gamma 1, 2. Okay, so I'm almost out of time. So let me just, I didn't finish everything I wanted to, but I'll just make one statement and say, so what is associativity? Associativity is the statement that you have the tetrahedron. If you have simplices gamma 0, 1, gamma 1, 2, you can first combine them to get gamma 0, 2. And then you could take another simplex gamma 1, 3 and multiply gamma 0, 2 with gamma 1, 3 and choose a composite of those two, which will give you gamma 0, 3. That's one possible way to do it. But you could also have done the other way around. You could have gone, you could have instead composed the other way. You could first have chosen a composite of gamma 0, 1, gamma 1, 2. Oh, sorry. I apologize. You could have chosen the other two faces, so I'm doing it wrong. You could have chosen the face. You could first combine gamma 1, 2 with gamma 1, 3 to get gamma, some element gamma, what would this be? This would be 1, 3. Oops, I think I've got the indices. Sorry, this is 2, 3. This is 1, 3. And this would be gamma 1, 3. Gamma 1, 3. And then I could combine, so I could first multiply these two and then multiply this with gamma 0, 2 to get this face. And the fact that you can fill in the tetrahedron tells me that these two ways give me the, it witnesses the fact that the two composites are in fact equivalent. So I think I'm out of time, but okay, to summarize, every topological space X gives rise to a, oh sorry, did I say weak Kahn complex? It's just a Kahn complex the way I defined it. I'm sorry. Is a Kahn complex. I apologize. So every topological space gives rise to a Kahn complex. Sing X, which can be thought of as the fundamental infinity groupoid, as an infinity groupoid, which is called the fundamental infinity groupoid. The fundamental infinity groupoid of X, sometimes written as pi less than or equal to infinity of X. Okay, so yeah, so I'll stop there because it's already 7, and I can just continue since I have the time from there.
So any questions?
Sorry, was that, yeah, I don't know. Was it too fast, or is there some definitions I can clarify? It's quite technical stuff, but the ideas are very simple. So I mean, if you haven't seen categories and pre-sheaves and so on before, it might be a little new, but the basic idea is contained in these pictures that I'm drawing, which is to say that you're trying to define a composition. You're trying to model paths and homotopies between paths and so on in the space, and you're modeling that combinatorially by saying that you have points. You have one simplices, which are paths between points, and you have two simplices, which are triangles, and so on in the space. So they're homotopies between paths. And the structure of a simplicial set tells you how all those things fit together, right? And yeah, so that's the summary. I mean, that's what this talk is about, and it's all contained in these pictures here that I'm trying to draw.
Sir?
Yeah.
Sir, on that very page, the way you have extended F to F tilde,
yeah.
So it will, I mean, quote unquote, look just like F, right? Because
it's
been composed.
Yeah.
F1. Yeah.
So I'm saying there is one possible way to extend it. You don't have to take that way. I'm just giving a proof that there exists one possible way, at least, to extend it. Because the definition of a Kant complex just requires that there exists a way to extend it. But the advantage of this is that I don't have to choose this particular way. I could choose a way that looks more like the one in the picture I've drawn over here on the right. So let's see, there's supposed to be some, yeah, the one over here. I have this picture here. And this, I actually have a triangle. So I actually have a non-trivial homotopy in this picture. So that means this particular picture I've drawn is not obtained by the construction of taking the retract and composing with it. It's something more non-trivial. And that's part of the flexibility that this affords you. So yeah, composing with the retract is just one possible way to extend. And so even in the end, when I'm thinking of this as an infinity category, as something where the points are objects and the paths are one morphisms and so on, I said that if you have two paths, you can view it. You can think of a triangle in the space, a two simplex in the space, as being witnessing the fact that gamma 02 is a composite of gamma 01 and gamma 12. So it's not equal to the composite, as in if you ran the first path and then run the second path, that's not equal to gamma 02. But this two simplex sigma is like a two morphism, which witnesses the fact that gamma 02 is one possible realization of a composite of gamma 01 and gamma 2. That's how we think about it. So the composition is not defined on the nose, it's defined up to some ambiguity. But that ambiguity is, the set of all possible ways of defining a composite is contractible. So that ambiguity doesn't matter, is what happens in the end. But that's exactly what an infinity groupoid is. It's something which has this ambiguity, but the ambiguities cancel out at me. So if I have two different composites, they will be related by a tetrahedron. There will be a tetrahedron whose one face is the one witness for the composite, the other face is another witness, and there'll be a homotopy between them. and so on and so on. So the ambiguity sort of like disappears if you go to high enough levels of simplices. Yeah, sorry, there's some chat. So there's a question in the chat, is there any concept of an infinity groupoid associated to any simplicial set? Yes, in a sense, the way I defined it, yeah, there is. So good question. So this is a bit technical. I won't have time to. Okay, so here's one way to define it. You take the geometric realization of the simplicial set, start with an arbitrary simplicial set. Okay, and the question from Alok is there a concept of an infinity groupoid associated to this simplicial set? The answer is absolutely yes. You take the simplicial set, take as geometric realization, that's a topological space, and take singular simplices on that geometric realization. That's a Kahn complex. That's the fundamental infinity groupoid of the simplicial set. That's a kind of very brute force way of constructing it. That's one way of constructing it. But there's a more sort of general way of talking about these things, which is to say that there's a model structure on the category of simplicial sets, which is some way of doing homotopy theory with simplicial sets. And in that model structure, the fibrant objects are the Kahn complexes. And every object can be replaced by a fibrant object that's weakly equivalent to it. Okay, so I haven't defined these notions, but I mean, I'm assuming maybe you know more about this. So from the question, so every simplicial set has a fibrant replacement, which is weakly equivalent to it, meaning, for example, the geometric realization of that fibrant replacement will be the same, will be homotopy equivalent to the, weakly homotopy equivalent to the geometric realization of my original simplicial set, and which you can think of as, so the fibrant objects are exactly the weak Kahn complexes, so you can think of this as being the fundamental infinity groupoid of the simplicial set. And one way to construct it is what I said. You take the simplicial set, take its geometric realization, and then take singular simplices on that. So in fact, the statement is that this adjunction that I defined is, I didn't get to talk about, I'll talk about that more precisely next time, but this adjunction that I defined is an equivalence of homotopy theory. So although topological spaces are not at the point set level the same thing as simplicial sets, they're not even equivalent as categories, but they become equivalent if you invert homotopy. If you identify homotopy equivalent topological spaces and you identify homotopy equivalent simplicial sets, there's a notion of homotopy equivalence for simplicial sets, weak homotopy equivalence. So topological spaces up to weak homotopy equivalence are the same thing as simplicial sets up to weak homotopy equivalence of simplicial sets. So as homotopy theories, there are two different ways of thinking about homotopy theory. You can either do that completely with simplicial sets, or you can do it completely with topological spaces. And most algebraic topologists actually work with simplicial sets and not with topological spaces for many purposes. So that's one way to interpret Poincaré's statement, if you like, and, that you don't need point set topology for this.
So I just noticed a small tidbit that this Daniel Kahn, after whom this is Kahn complexes are named, is born on 4th August and died also on 4th August. He doesn't have anything to do with it.
I see.
Nice talk.
Strange, very strange. Thank you. Yeah, yeah, go ahead.
Hi, thanks for the very nice talk. I was just wondering if the notes are also available some way or the other.
Yeah, I can share this this PDF
online.
I can email it to Anita maybe or something.
Okay.
Yeah, I'll try to upload it by tomorrow.
Yeah.
You can. You can access ISI website. I'll try to upload it there. Even the video should be uploaded by tomorrow.
Okay, thanks. Thanks once again for the nice talk.
Oh, thank you. Yeah, I have to say I'm sorry about my handwriting. I'm not used to writing. I mean, I'm used to writing on the slides now, but it's never the same as writing on a real blackboard. So my handwriting here is kind of little hard
It's
to
a
read. Maybe,
geometric realization of your thoughts.
yeah, yeah. So yeah.
Okay, so if there are no more questions, then we'll call it a day. Thank you, Pranav. Thank you so much.
Yeah. Yeah. Thank you for having me.
So the next talk is on 3rd of December. That's Friday, same time. That's 5:30 p.m. And you can use the same Zoom link to log in.
Great. Yeah. Thank you. Thanks, everyone.
Thank you. Thank you so much.